Welcome to Ask and Learn.
In this problem, we're dealing with a roller coaster, and we want to find three different things. So we want to find the initial height of the hill at point A, so that the cart on the roller coasters can go through both loops. And we want to find the normal force the cart experiences at point B. We call that FNB, and also the normal force at point C. We'll call that FNC. And we're told that initially the cart has a velocity at the top of the hill. We call it VA, is 3 meters per second. So since we're looking for a height, that means the cart is going to have a potential energy. And if the cart has a velocity, it also has kinetic energy as well. So since we have kinetic and potential energy, we can look at conservation of energy. And we can break this up to just looking at point A, the top of the hill, to point B, the first loop. So we have initial kinetic energy plus initial potential energy equals final kinetic plus final potential. Just expand this, and we have 1/2 m, so the initial is VA squared plus mg HA is equal to, so the final kinetic is when it reaches point B, so 1/2 m VB squared plus the final potential is at point B, so mg HB, and HB is given to us. And so what we're looking for in this problem, in this equation, is the velocity. So to do that, we look at a free body diagram of the cart at point B. So we know that, look at the cart upside down, what's pushing you down to fall off the cart is the centripetal force. Pointing down is the weight, and also the normal force. And the weight of the cart is just mass times gravity. So if we do some of the forces, we have the weight, mg, plus this normal force, FNB, is equal to the mass times the acceleration here is centripetal acceleration, since there's a centripetal force. And when the cart leaves point B, we can say it experiences a 0 normal force. So FNB will equal 0. And that's one thing we're looking for. So if we keep going, we have mg, the weight, is equal to mass times centripetal acceleration at B, which is VB squared, divided by the radius of curvature, and that's also given to us as well. So it's half the height. So we know that the masses cancel. So we solve for VB. We have VB is equal to the radius of curvature, 7.5, times gravity, 9.8, and then square root to get rid of the square. So VB is 8.5 meters per second. So we can plug this back in and now find the height HA. And also plug in the numbers we know. So 1/2 m, 1/2 of the mass. The mass is 700, so we have 350 times VA, the velocity, which is 3 squared, plus the mass, 700, times gravity, 9.8, times the height HA, which is what we're trying to solve for, is equal to, again, 350, the mass, times the velocity VB, which we found, 8.5 squared, plus 700, the mass, times gravity, times the height, hb, which is given as 15. So let's clean this up a little bit. So on the left we have 3150 plus 6860 HA equals 25,287.5 plus 102,900. So we keep going with this. So we add stuff on the right and then subtract 3150. So we got HA equals 125,037.5 divided by the 6860. So for the height, HA, we get 18.2 meters. Now to find the normal force at C, we can break that down as well. So the normal force at C, we can look at from points B to C. We know at C the force will be the weight of that car, mg, plus that normal force, FNC, equals, again, the mass times the centripetal acceleration, v squared at C, divided by the radius of curvature at C. So what we want to find now is the velocity, so that we can solve for normal force at C. So again, we look at conservation of energy from B to C. So we have the kinetic energy at B, 1/2 m BB squared, plus potential energy at B, mgh B, equals kinetic energy at C, 1/2 m BC squared, plus potential at C, mgh C. So again, we're solving for VC. So now we plug in our numbers. So 1/2 m is 350 times VB, which we know 8.5 squared, plus the mass 700 times gravity 9.8 times the height, which we know 15, equals stuff on the right, which is 350 BC squared plus 700 times gravity times the height at C, which is given as 10. So now we can clean this. We can solve for VC by plugging all this into the calculator, and we get VC, the velocity at C, 13.1 meters per second. So now we can plug this back in and solve for the normal force at C. So we have the normal force at C is equal to, and then we move the weight to the right side. So we have the mass, which is 700, times the velocity at C, we just found 13.1 squared, divided by the radius of curvature at C, which is 5, minus that weight, which is mg, 700 times 9.8. So then finally, the normal force at C is 17.16 kilonewtons.